Okay, I'm going to find the area bounded by these two functions. I have a simple upside down parabola, and then I have the natural exponential function. And the tricky thing about this problem is that there's no analytical solution to this equation, e to the x equals 2 minus x squared. I can't get this symbolically and find the intersection points of the curve. So I'm going to have to do this using technology. So I'm just going to call this x1 over here. It's some number between -2 and -1. And then x2 over here, some number between 0 and 1. And I'm going to do this in wxMaxima using the find root function. So what I need to do is express this as e to the x minus 2 plus x squared equals 0, because what Maxima can do is tell me where a function is going to be equal to 0 by using a numerical approximation. So let's go to Maxima, and I'll go ahead and type in my function like this. Oops. I'm in a bit of a jam with all the stuff on my desk here. So I have percent e to the x, and then I have minus 2, and then plus x squared. Just double checking real quick. Yes, okay. And I'm going to use the find root function. So I'm going to go find root for this function f of x on the interval -2 to -1. That's where I saw one of my roots. And I get -1.316. Then I look for the next one on the interval 0 to 1. So we'll just toggle back to Maxima and just change that lower bound to a 0 and the upper bound to a 1. Hit Shift Enter, and I get 0.537 for that one. Okay, then we're ready to get things set up. So I look at a little area element here. That little area is very well approximated by a rectangle. It has a width of dx, and then the height is going to be the difference in y coordinates between these two curves. So that's going to be 2 minus x squared minus e to the x. And I can get my integral set up. So I like to write down the name of the little differential area that we just drew over there. So that's dA, and it's going to be height 2 minus x squared minus e to the x multiplied by width dx. And then to get the total area, I use the integral as a summation device to add up all the dAs. And I am adding up dAs all the way from x equals -1.316 to 0.537. And these are all easily guessable, so I get 2x minus 1/3 x cubed minus e to the x. E to the x, that is that special function equal to its own derivative. And then I evaluate from -1.316 to 0.537. So there's going to be a bit to plug in to our calculator here. All right, after crunching all those numbers, I ended up with 1.45 for the area, and I wanted to point out that you can check for the reasonableness of that on the graph. So up here in the graph, these grid squares each have 1 unit of area because they're 1 by 1. So I just have to look at the shaded area and ask myself, is it plausible that that's about 1.5 squares worth of area? And it looks pretty good. If I cut off this little chunk over here to the right of the y-axis and pasted it over here, that would be about 1 square. And then this little chunk over here, that's about half a square. I would slice off that little sort of triangular piece and paste it here. Looks like about a half. So about 1.5 squares, yeah, that looks reasonable.